All right, thank you very much. I think it says host disabled participant screen sharing.
Yes, you can try now.
Again, yeah, great.
Okay, so it's working, right?
Cool, yes, it is working.
Okay,
thank
great.
you very much.
Yeah, okay.
Let me just start sharing. Cool. Okay, so yeah, my name is Sergio Garrido. Well, before I start with the presentation, I would like to thank Claudia and Robert for inviting me. I'm really honored to be part of this. It's very cool, and I think it's also very cool that we were talking about it before with Claudia and Robert. It's very cool that these presentations basically are democratized and that we're all able to learn from this. This is pretty cool. Now, a little bit about me. I'm a PhD student at DTU in Denmark. I'm at the transport department, and I'm working between two labs, the machine learning for smart mobility, which you have in here, and the demand modeling group. So basically what I do is I use a lot of machine learning methods to solve some transportation problems. Apart from that, I'm on a leave. I'm an Amazon PhD research intern at the Causality Lab in Tübingen. And although this project is related to causality, I did this before I joined Amazon. And this is at the moment under review at the Journal of Causal Inference. There is also an archive version, although it's a bit outdated. So probably in a couple of months, there is going to be an enhanced version. All right. So what I'm going to present today, I change a lot the title of my papers. I don't know why, but the title that I'm going to give you today is Estimating Causal Effects Using Neural Autoregressive Density Estimators and Calculus. This is joint work with Stanislav Borisov, Yeperich, and Francisco Pereira. The presentation is going to be divided in roughly 3 parts. So I'm going to explain a lot about causality because I know this is a deep generative modeling meetup. So I know that you know a lot about deep generative models and neural networks, I guess. Then I'm going to explain a little bit about the method itself, so the neural autoregressive density estimators, and I'm going to show a bit of preliminary results, very basic results from simulated data. So let's begin with what is causality itself? What is the definition of causality? So if you take the Merriam-Webster definition, so online dictionary, it says it's a causal quality or agency. The second one says the relation between a cause and its effect, or between regularly correlated events or phenomena. I just read it. So, causal, you want to define causality and you have to use the word causal, or then the second cause and effect, or even it says between regularly correlated data, which is actually not correct. So basically, during the last 35 years, let's say, statisticians and computer scientists, such as Pearl, took kind of on the task of defining causality in a more mathematical way so that it can be explored also with data. There are 2 main frameworks of causality. One is the Rubin's potential outcomes. The other one is Pearl's do calculus or graphical models, structural causal models. And these 2 are the most famous. Of course, there are other ways in which we can think about causality. For instance, the Philip David statistical decision theory kind of causality, or causal decision theory, which doesn't even have counterfactuals, which we're going to talk about in a minute. All right. So this kind of the frame in which we're going to think about with this paper is only with Pearl's causality. And what I'm going to explain now, it's with Pearl's causality, but I must say that between Rubin causality and Pearl's causality, there are a lot of places where they are similar, and most of the things that you can say in one language, you can say in the other language. Now, Pearl's causality. By the way, for those of you that are interested in knowing a little bit more about this causality stuff, I really can recommend this Book of Why by Julia Pearl. This would be kind of the easiest way to learn about causality, and it's a very readable book. All right, so what is Pearl's causality about? So it's based on 2, let's say, main tools. One is the tool of graphical models, and the other one is the tool of structural equation models. So for those of you that know a little bit about probabilistic modeling, graphical models are the usual way in which you can represent probabilistic models. And for instance, I remember that I think during the last meetup, you saw a little bit of VAEs. For instance, the VAEs are represented even in the original paper as probabilistic models, as graphical models. And then the idea, the difference between these probabilistic models and then the kind of these causal graphical models is that there is a true causal graph. And by true causal graph, it means that the topological ordering of that graphical model, of that graph, is the actual topological order in which things happen. So you can think it in a quintessential example is that, let's say, first it rains and then the floor is wet, and not in the other way around, in which the floor is wet and then it rains, right? Now, there is a subtlety here, which I wrote, which is this Markov equivalence class. And what happens is that from observational data itself, so from the data that you collect, that you observe and you collect, it is, you need to make some assumptions on this topological ordering, because otherwise they can give you, let's say, the same likelihood, or they can have the same properties regardless of what is the ordering. Okay, and the third really important concept from Pearl's causality is these three ladders of the causal hierarchy, let's say. The three ladders represent different queries that you can make, causal queries that you can make. The first query is this conditioning query. The second one is intervening, and the third query is doing counterfactuals. I'm going to explain that in detail, but just kind of to tease a little bit what is going on. What people usually do when they do, let's say, deep neural networks or regression trees and very powerful models, they usually do conditioning unless they are very explicit, unless they're being explicit about being causal. All right, so let's take a look at the three possible operations. So let's assume that we have this graph in here. We have 5 variables, A, B, C, and D and E. And let's assume also that this is actually the proper causal ordering of variables. So meaning that, as I said before, let's say A is that it rains, and then B might be the floor is wet, C might be, I don't know, the water, the plants are green if it's spring or whatever. Anyway, this, the graph on the left, this represents a conditioning query. So let's say you can ask this type of model, what is the probability of E given that you observe B? You could also observe, let's say, A, and then ask on a query on E or whatever other variable. But it's important to notice in here that conditioning in B in this case is not the same as setting B to a specific value. That means that the belief of E or the probability of E is going to be affected by both the direct effect of B through D, but also by the indirect effect of B through A. Given that you don't observe A, then there is also an indirect effect through what is called a backdoor. We're going to talk a little bit more about that. So I don't know if you want to learn more about this, about how does this even happen, I recommend you to read a little bit about this concept of de-separation in graphs. So basically, how do you get these conditional dependencies and conditional independencies given some observed variables on the graph? Now, let's look at the second type of operation that you can ask these models. The second operation is this do operation. So this is basically, what if you can go into the system and set a variable into something? So let's say that you had a rain machine, and then you say, okay, well, there is going to be rain right now. So then you can also ask what would happen to a certain variable, right? So maybe D or E, whatever that is, then you can, after setting the variable to some value, then you can ask for the probability distribution of another variable. And in this case, there is not going to be this backdoor, let's say, in which the information would flow through not observing A, basically. Now, if we could all go and intervene into any variables or in any system that we're interested in, then kind of this problem is solved, in the sense that, you just go, you intervene, and then you just check what would be the distribution of the variable you're interested in. But if you can't go and intervene in the system, you have to do something about it from observational data. This is what I was talking about before. So you go and you observe a system, something is happening in the system, and you want to make some basically interventional queries out of this. And this is very obvious from the rain example, for example, but also in medical examples where we're interested in causal inference as well. You can't just go and say, yeah, you have to smoke for 15 years and then see what happens, right? This for ethical reasons and for logistic reasons, this is impossible in many, many settings. Now, the last of the queries, which is this counterfactual, this is a bit more complicated, and actually this can't be represented in a simple graph like this. So let me first start with an example, and then I will go into kind of what is operationally what we're doing in here. So the example of something we would like to ask now with a bit of relevance with the American elections is, so given that Joe Biden won, we would like to know what would have happened if Joe Biden had gone to Texas, let's say 5 days before the election. These are the types of a query. But it's interesting because in this case, you're conditioning on something that you already observed. You are doing a query on something that you already observed, if that makes sense. So you're asking what would be the outcome of the election, given that Biden won. So in theory, if you think about it, it's like, okay, but you already know that Biden won, so how does that work? So this is kind of the counterfactual part of it. And then what you do basically is that from this graph in here, actually, I don't know if you can see my mouse, my pointer, can you? Ah, yes, you can, thank you. So what you do is that let's say you observe a certain variable, in this case, is going to be Biden winning, and then you're going to infer, so you're going to go back into the graph and observe and let's say make a guess of what would be the distribution of the rest of the variables. And then again, as in the second query, you're going to propagate some intervention and see what would happen in E. In this case, you can't see this in this graph because you need to use another type of machinery that are called the structural causal models that I mentioned briefly before. You can also use the concept of twin networks, single word intervention graphs. There are a lot of different machineries that you can use. For the purpose of this paper, we're going to focus only on the second type of query. So as I said, this first query is the thing that we usually do with deep generative models, with the neural networks, whatever. The second one is usually not the thing that we do. And then this third one is a bit of a more complex monster than this one. All right. So what would I say lies in the heart of causality? And if you want to take away a single thing from this presentation, is this equation from here. So let's call our set of variables X. And the point is that we can represent the joint distribution of our variables X by a factorization or a Markov factorization of our variables given their parents on the graph, on the real causal graph. And each one of these distributions in here, each one of these conditional distributions in here, they represent what are called usually the independent causal mechanisms, and they work as modules. They work as modules of these graphs that we have in here. So in what sense? So what am I trying to say in here? So basically, this row represents one conditional distribution, which is going to be basically the probability of B given A. And this one, for instance, is going to be the probability of D given B and C. And each one of these are independent causal mechanisms, and these are the basic, let's say, objects with which we work in causality. Now, maybe for those of you that already know a bit about these neural autoregressive density estimators or these autoregressive estimators, you'll see that there's also already something in here. And yeah, so this is actually, I don't know if this is such a good graph, but then what I try to say with this is that you can use causality as an inference machine. What does that mean? You input some causal assumptions, and the causal assumptions come in the form of a functional form between the variables, which variables come before which other variable. There's a lot of queries that you can make, and the machinery of causality is going to tell you, okay, in order to compute a certain interventional distribution, or in order to compute some counterfactual, these are the independent causal mechanisms that you need to compute. And then you have to play with them a little bit with something that is called a do calculus. I saw that someone sent something on the chat. I don't know if I should take it. Or?
Oh, it's me. I just put a resource to a course on.
Okay, okay, yeah, great. Yeah, okay. And now I'm going to give you the problem and the solution. So if you go into the causality book by Pearl in 2009, and if you also go to the book of why, which I just recommended, they don't tell you how to estimate these independent causal mechanisms. So these are called, so the assumptions that are made in there are basically, these are not called non-parametric probabilities. So basically in the limit of infinite data, what you can do is you compute relative frequencies, right? So if you have, if you flip the coin 1,000 times, then you see the amount of times that it landed heads, and then that would be the probability of heads. But then if you think about it, you usually don't have infinite data, and most of all in these critical applications, wherever you have, health data or even like weather data, you have actually small amount of data, or not so big amount of data. And so we need to find a way to estimate that thing. And of course, causality is not completely new. In economics, it has been worked for a bit, and in epidemiology and other medical sciences, they have worked with them as well. But the problem is that they usually have to make extremely simplifying assumptions on the other way in order to compute this stuff. So it is very common in economics, for instance, to do linear regressions, two-stage linear squares, but they're basically a linear relationship of the variables. And then if you have a little bit more of idea, of how the variables, might relate to the outcome, then, you compute the square of the covariate and then see what happens if the square worked or not. So this is already problematic. On the one hand, we have this very strong machinery of causality, and on the other hand, we have the estimation problem itself, which sometimes is not used properly, let's say. So the solution to this is to use any flexible approximator to estimate these independent causal mechanisms. So these independent conditional distributions. I may say that, I use neural networks because I wanted to use neural networks, but in fact, I have thought about any other estimator, and people in fact have already started using many other estimators. You can think, for example, of Gaussian processes, which are very, very flexible estimators, and which, on top of the fact that they are very flexible, they give you some uncertainty quantification, which, as you might know, neural networks don't give you.
Sergio?
Yes.
There is a question.
Yeah. Oh, yeah.
Are you reaching the questions?
Yeah, I'm reaching the question section.
Okay, so let's wait then.
Okay. So in order to make this inference, of course, as in statistics or any statistical inference, you have to make assumptions, and in causal inference, you need to make another type of assumptions. There are going to be three assumptions. The only very, very important here is that we actually know the causal graph. And this is, like, to me at least, when I was starting to learn about causality from the graphical models perspective, this was a big turn off, because knowing the causal graph, I think it's something impossible. But now that I'm working on my internship and working at a company, I realized that there are a lot of people that maybe don't know about machine learning specifically, and then don't know about these estimation methods, but they do know, have a lot of expert knowledge of what would be the processes and how the system works. So, if you're talking about logistics, then you have to receive from this company and maybe receive from this other company, but they also at the same time they receive from other places, and then you can actually build the causal graph from expert knowledge. The other two assumptions, which are not so strong, but you still need them, is this assumption that we know the distribution of the variables on the graph. So let's say if you have a binary variable, then you have to say, okay, this is a Bernoulli distributed variable. Or if you have a variable on the reals, then you have to say, okay, this is a normal variable. But then don't worry about this. This sounds very strong as well, but I'm going to give you a solution for that. And the last assumption is this acyclical. So that means that in the graph that we saw before, we can't have D causing A and A causing D, or any type of cycle in the graph. This is not so complicated, given that if you, for instance, have some causal graph, which is like, there's a lot of dynamics in the causal graph, then you can always unroll the graph. It's called what it's unrolling the graph. All right, so this is a little bit of the causality part. I will take some questions. Let me see. Yeah, I can open the chat. Okay, does causal inference approach? Yeah. On weightings of the variables. Maybe, I don't know if participants can unmute themselves, but what do you mean by weightings of the variables?
They should. They can unmute themselves, by the way.
Hi, Aiden. Okay, I guess if you want to expand a little bit on the question, I can tell you later, or you can also send me a message. But I am not really sure about what you're saying on the weightings. Well, maybe actually I do know what you're saying about the weightings. By weightings, maybe you mean by weightings you mean that whether B is more important in D than C, maybe. I guess that would make sense if we were talking about the weightings. No, the causal inference approach doesn't tell you that, and that's actually kind of the important part of this of the estimation procedure, because what you actually want to know and understand is which one are the most important variables, so which one have more weight. I hope that that helps answering your question. And what Python package do you recommend for PGMs? So I have in the past used, so the probabilistic programming is also a very, very exciting area of research. I have used Stan and I have used Pyro, and both of them are very cool. But if you're interested, of course, in this neural network stuff, Pyro definitely, because Stan at the moment is not so neural network friendly. But they're both very, very cool packages. All right, so I'll just keep going, and then I'll tell you a little bit about the neural autoregressive density estimator. Actually, before I start with the neural autoregressive density estimator, I'm going to introduce you to the graph that we're going to work with today, and this is the graph here on the left. So this is a very classical causality graph, and basically it's 3-variable graph, where you have this in the medical example. So you have kidney stones, you have treatment, and you have a recovery variable. And then, you know, kidney stones can be large or small, treatment can be A or B, and recovery can be recovery or not. But of course, you can make them continuous if you wanted to do that. And let me show you what these neural autoregressive density estimators are. So neural autoregressive density estimators, they are basically neural networks models that aim to compute basically this thing in here. However, the basic difference with what I've been talking about so far is that they usually are order agnostic. So what does that mean? That they don't care about what the true graph is, but they just, let's say, randomize the variables, and they say, okay, so this one takes as input, takes as parent, let's say, KS, but maybe then R takes as parent, KS takes as parent R. It doesn't matter. The ordering of the variables doesn't matter. And how do you estimate this? Well, basically, the most basic case, which is the one that I'm going to present in here, but I'm going to talk a little bit more about other approaches. The most basic case is the case where you have an independent neural network for each one of the variables. So that means that, let's say, if you, in our case, if kidney stones doesn't take anything as parents, then it just takes a 1. So this is a fixed point neural network. But if you have this T, then the treatment variable, then it will take a KS as input. And then you basically model the parameters of the distribution as the output in here. And what does that mean in practical terms? That if your variables are binary, and this maybe will help you remind from the assumptions that we made. If the variables are Bernoulli distributed, then you're just going to have a parameter P in here. It's going to be a P, and then you can optimize this by negative log likelihood. So I guess that negative log likelihood, I'm going to assume that everyone knows how the training procedure works with negative log likelihood. It is very similar to having any other loss function, right? So you just have a distribution, and as long as the parameters are differentiable in the inside the distribution, then you can optimize that by usual backpropagation. And so in here, in the example, let's go back again to how does this look in like in the practical form. Basically, we're going to take we're going to have the parameters of kidney stones by itself, treatment condition on kidney stones, and recovery condition on both kidney stones and treatment. And then the joint distribution is found in here, and also the Markov factorization of the distribution is found in here. All right. There is another question in here. So it says, does causality inference hold primary for a single factor initiating the causality? What about dual variables having equal impact? So yeah, I think these are important questions. But then again, I think these are questions about the inference itself. So as long as you know what is the ordering of the variables, regardless of the functional form, you can tell which one is the important variable. And now, if you think about this factor initiating, so what I'm guessing is that you're thinking about something that is, let's say, above kidney stones, you know, maybe some health-related risk stuff, and then whether this affects the recovery in the future. So through kidney stones, how does that affect the recovery? Yes, there are some methods in which you can say, okay, so recovery changed this, you know, this percentage or whatever. And then how much can you attribute that to a change in kidney stones, or how much can you attribute that to a change in health risk-related stuff, let's say. Okay, so let's continue. Okay, and basically there's a whole bunch of models that have been working in this area. So you have, you know, starting from a Turing Prize winner, Benja, model high dimensional data, you know, you have this La Rochelle, this NADE, neural autoregressive density estimator. You have this one was only with binary variables. The next one, you're allowed to have continuous variables, and you're allowed to have continuous variables basically by modeling this with a mean and a variance of a continuous distribution. So that's, you know, simple extension. And, you know, you have this one, for instance, the last one is looking for a way in which you can do the computation faster and more efficient. And then you also have these pixel CNN, which are super fancy and nice methods. But we focused on this work on the simple case. Well, first of all, because this is it was a proof of concept at the time, and we wanted to see whether this would work or not. But there are other reasons associated to estimating the neural networks independently, as opposed to finding the most efficient, let's say, way to estimate. And basically, kind of one of the motivations is related precisely to these independent causal mechanisms we have in here. So if we estimate independent neural networks, then we're going to have that. And if we want to generalize, let's say, to other population or other data, we can take maybe these single neural networks and put it in other places. All right. And okay, this sounds pretty cool, but why people don't use them that much as compared to, you know, VAEs, GANs, and all these latent variable models like normalizing flows, which are also very cool, but these tend to be very well. Well, the problem is that at generation time, these are extremely slow. So think about the process of generating from this. If you wanted to generate an observation a full observation, so a full person that had kidney stones at treatment and recovery, what you have to do is you have to propagate first to the first neural network, then to the second neural network, and then using the input from both of these, then you have to propagate into the third neural network. And then, of course, if you think about this, and if you think, you know, in the space of images or speech or whatever, then this can take very long time to generate even only one observation. So kind of we see the trade-offs in here. On the one hand, if we're thinking about images and if we're not thinking about causal problems, then this is not very useful in the way it is. But since we're thinking about causal problems, then this basically does the job and actually maybe has some other interesting properties, which we don't have if we think about it only from the efficiency side. Okay, So let's go back to causality before some questions that we're going to have afterwards. So the table of the observed data of this kidney stone example is this one that we have in the right. There is something very interesting about here, and this is called the Simpson's paradox, and this has motivated a lot of, even Pearl says, I don't know if that's true, PhD thesis. So this Simpson's paradox is, as you can see here, you have the treatment type, you have the size of the kidney stones, and then you have the percentage of people that recovered. And then as you can see, people, if you assign treatment both to people with small kidney stones and large kidney stones, they have a higher recovery rate than treatment B. But if you take treatment B as a whole, then the recovery rate is better than treatment A. So that, of course, is not consistent, and this can't be in this way. And basically, the problem here is that the estimates that you're doing in here, they're not adjusted. Of course, you can check these numbers. These are, this is, let's say, this is a real example. This is from real data. So you can bake these examples by using some statistical properties, but this happened in a medical paper. And again, coming also back to the fact this experimental data versus observational data. So if we have observational data and we can't go into the system and maybe say assign a treatment, intervene on the treatment because the testing period already passed, what you need to do is use this machinery of the do calculus that Pearl used in order to get the interventional distribution out of that. So the interventional distribution in this case, for instance, we're going to be interested in what is the probability of recovery, given that we assign a specific treatment, which in this case is going to be A. And the way that you estimate this thing is by this formula, which is called the backdoor adjustment formula. And basically what it does is blocking the effect that the treatment has on recovery through the kidney stones. So if you remember when I was showing the first graphs, I was telling you that if you condition only on B, it was the case, then you would have some effect through the variable A. So basically what this backdoor adjustment formula does is adjusting by this effect that is going on in here. Unfortunately, I think we don't have enough time to go through the whole derivation. It is not so difficult, but it's not trivial either. If you want to know more about this, absolutely go and buy the book of Y or read it wherever. But it's very cool and it's very interesting, the things that are being done here. All right, so maybe second round of questions.
Yeah, maybe I have a question. So
yes.
Like if you do share representation
yes.
into the multi-layer perceptron, so
yes.
how fast would that be? If you, orders of?
I wouldn't expect. So in this, at least in these two examples, I'm absolutely sure that there is no gain in that, because these are two examples, these are extremely small. Now, if you could come up with a causal graph big enough that you have to do this sampling, one by one, then it can be complicated. Now, to be fair, there are, this causality stuff, this has already, as I said before, they have developed it a lot, and there are causal graphs which have hundreds and thousands of variables from medical data particularly. So there are these graphs that were created by doctors all around the world. Let's say, okay, if you have this symptom and this symptom and this symptom, then you have to propagate forward and so on. And then if you used a neural approach to do that, then it might become complicated. And these usually, I don't know, maybe some of the people here are aware of this, they usually do this with the classical belief propagation. So they do it more in the non-parametric way to work with these graphs. But for this example, I wouldn't expect like too much gain. Now, the thing that you have to take into account, maybe to complement a little bit the answer, is that these, as I said, these autoregressive density estimators, or these neural autoregressive density estimators, they tend to be slow, mostly in the domain of images and speech. And this is because of the characteristics, right? So if you think about how an image is, maybe a small one is 32 by 32 pixels, and then if you have to do that pixel by pixel, then of course it's going to be extremely slow because you're working on a 32 times 32 space in speech in the same way. But then if you're working with, let's say, tabular data, this is never ever a problem. And I think that probably no one will ever come up with a no. This is too much saying. I think this is a bit harsh. So I find it very difficult that someone would come with a pixel level causal graph, if that makes sense. Because what you would need in that sense is you would need to have a causal graph that says, you know, pixel on the coordinate 5, 5 causes pixel on the coordinate 5, 7, and then that one causes that, and maybe that takes some other as cause. I find it extremely difficult that someone could come up with a causal graph of pixel level. Does that make sense?
Yeah, it makes, yeah.
Yeah. All right.
And maybe another question is about the backdoor stuff that you mentioned.
Yeah. I can come back if you want.
So this basically blocks one node
to
go. So it blocks the node. Okay.
Yes. So this is blocking the information coming from the kidney stone into so the information that comes from the treatment through kidney stones into the recovery. So this is what this formula is doing in here. And this, I forgot saying that, and I think that's very, very important. This is called a confounder in the causality literature. This is called a confounder. A confounder is a variable that is causing two variables at the same time. And what you usually want to do, so you were going to read if you're interested in this stuff, is finding ways of deconfounding. So finding ways of blocking the effect of that variable that is causing both variables at the same time.
Okay, thank you.
All right. And okay, so maybe that's a great question actually for something that I'm going to be mentioning later. And that's the fact that if in this causal graph with 3 variables, you didn't observe the kidney stones, there wouldn't be any way in which you could estimate the effect of the treatment on the recovery variable, because you need to do this type of adjustment for this type of graph. So unless you could go on the system and experiment on the system and act on the system, then you wouldn't be able. It's just impossible. And then you would get this effect that we have on the table here.
All right. There is another question in the chat.
In the chat? Okay.
Yeah, in the chat, yeah.
If time permits, can you comment again on what happens when we have a Bernoulli distribution? Had no someone line with, okay. So yes, with Bernoulli distribution, the thing is, this is more oriented in how the output of the neural network looks like. So what you're doing with these neural networks is something that is called neural density estimations. If you want to check, I can highly recommend the mixture density networks by Christopher Bishop. But the idea is very simple. What you have is a certain input of the variable, and then as the output of the neural network, you're going to have a parameter of a distribution. If you have a Bernoulli distributed variable, so if you have a binary variable, then what you have is just a logistic output, right? And then that's going to give you basically the probability that that variable is takes a certain value. And then you can always train that. So the way you backpropagate through the network is by estimating the negative log likelihood. So this P gives you some log likelihood, and then you want to maximize the log likelihood, so you can always propagate the negative log likelihood too. You want to minimize the negative log likelihood. But to make it a bit more complex, if you want, if you had real valued variables, then you can also output the mean and the variance of a normal distribution, and you can also backpropagate through the negative log likelihood of a normally distributed variable, as long always as the distribution, the probability distribution is differentiable with respect to the parameters. That's the condition. And this, if you think about it, this is basically the principle of VAs. Maybe you know about VAs. So in VAs, what you have in the encoder, and both in the encoder and the decoder as well, in the encoder, what you have is you have some input variables, and as the output of a variable, as the output of an encoder of a VAE, you have a mean of a variance of a distribution. However, in this case, in the case of the VAE, it's a posterior distribution, while in our case, we have some distribution of observables. I hope that answered your question, Ivan. Okay, I'll just keep going. Okay, so I'm going to tell you about the simulation studies. This is the last section of the presentation. We're just going to. So we did 5, 6 simulation studies. I'm going to show you the last 3. Why I don't show you the first 2? Because they're relatively simple. So basically what we showed in here is that neural networks learn linear functions as well. And we did this in order to prove, or to check the kind of proof of concept that that maybe we didn't introduce any statistical artifacts, let's say, by introducing neural networks in this kind of problem. So as I said before, a lot of times it is assumed that there is a linear relationship between the parent variable and the child variable. But so what we showed with this is that neural networks could learn also this relationship if this relationship was true as well. The second one is the same case. So we just change into a continuous random variable, and then you can use any differentiable distribution. Now, the third one is a bit of a more interesting case. We still used the linear effects. We still use linear effects. However, we estimated the effects. We generated the effects from different distributions. Let me see. Yes, we have the table in here. So this is, if you remember, the second assumption that we made in here is that whether we needed to know the distribution, the real distribution of the data. So in continuous data, this can be a bit tricky. And why? Because, you know, continuous data can be gamma, as you can see in here. They can be log normal, they can be normal, they can have a lot of different distributions that might not be consistent with the data. And then knowing the particular distribution of a variable, and most of all, if you don't have a lot of data, it can be a bit complicated. So basically what we want to prove in here is that regardless of the distribution that generated data, our model would be able to recover somehow the effects. So this ATE thing that we have in here is the average treatment effect. So basically what the average treatment effect is doing is taking 2 treatments, let's say treatment A and treatment B in this case, and just subtracting the probability of recovering, intervening on A minus intervening on B. So just checking the difference of those. And this is the analytical one, which we can compute from above. And kind of some data generating process that we made. But let me tell you what is the interesting part in here is that we generated 2 different types of data sets. In one data set, we generated this kidney stone using a gamma distribution, and the other one with a log normal distribution. So the log normal distribution, it's differentiable, and so you can train a neural network to learn a log normal distribution. However, the gamma distribution is not straightforward. So there are ways in which you can do it, and they're a bit complicated. You can do it, but it's too complicated. So we wanted to test, okay, what happens if the confounding is gamma, but we still use a log normal confounding? And what happens if we do a log normal confounding and we use the actual data generating process, which is a log normal confounding? So as we can see from here, of course, you know, these are just numbers. These are not telling you very well, like perfectly what's going in here, but what we can see is that they're relatively close to the actual effect that we're looking for. So even if we use the real log normal confounding, we don't get like specifically to the value 4 that we wanted. And even, but if we use the gamma confounding, we're not going to be very far. And this is going to point to something that I have mentioned in the past, which is basically, if you wanted to, you can model the output of any of these neural networks with a distribution as complex as you want. Particularly, to very complex way to parameterize these distributions is by using mixture density networks, so a mixture of normal distributions, and that will give you an arbitrarily complex distribution. Or you can also use, for instance, normalizing flows, which are very fancy and nice models. So, you know, they transform the distribution, they squish it and pull it and so on, so that you can arrive to very weird distributions. Okay, this is number 5. Yeah, number 4 or number 5, a simulation study. So what happens, of course, if we use a nonlinear case, and this is kind of the core of the problem, because what we wanted to see is that effectively the neural networks are able to find nonlinear effects in the data. So in this, you can see the generating process. We generated log normal. Basically this 15 here is just to keep it like everything in a relatively okay size-ish. And then what we can see is that if we see the neural approach versus, of course, the linear approach, it's just learn square number, and the true approach, we see that the neural approach, it's okay, it's doing well. More interestingly, I think, is how does the data support affect the output of the neural approach. So you can see that in this area, so okay, so on gray behind what we have in there is kind of the histogram of the data. So this means that where are the values of, actually I forgot to put the axis in here, I'm sorry. So basically this is the treatment effect. So this is what I was talking about before. And then this is the kidney size. I'm sorry, I forgot to put the axis in here. So this is the kidney size and this is the treatment effect. But then what we see is that since we have a log normal distribution, then we have this shape in here. And of course, there's going to be a place where the data is more centered into, and this is around, let's say, above 8 and below 17, more or less, approximately. And then you can see that in here, the treatment effect is approximately quite well. But then when you get too far away from the data distribution, then it blows. So basically it doesn't work that well. Of course, it's not as bad as the linear treatment effect, but I wouldn't trust this model very well, you know, maybe in the kidney size 3, whatever. So it's very interesting, and kind of these properties we still haven't studied very much on detail. However, this is relatively studied in causality, and there are some properties about the support of the data, how much data you have, and where is it distributed, where you have like these positivity constraints and so on. And so, okay, so maybe some people, they have heard already about causality and neural networks, and then you may say, hey, Sergio, you're not doing anything new. And the truth is that, yes, of course, whenever you want to do anything related with neural networks, someone else did it before you. That's always the case. But the way I differentiate from other work is basically by the fact that the other ways that neural networks have been used to estimate treatment effects and causal effects and so on is by using the potential outcome framework. So basically using this Rubin approach and not basically the Pearl's approach. And this is going to become important in the last simulation study that I'm going to show you right now, which is this case. So before I told you that if you have this confounder, if you don't observe this confounder in the graph that we had before, so ignoring this MG, then you will never be able to estimate treatment effects. Now, in the case in which we have these 3 variables in here, but we still don't observe the kidney stone size, then we can estimate the effect of the treatment on the recovery, even though there is information flowing from here. And basically what we're going to do is kind of block that information that is going to flow from T to KS and from KS to R. And this is called the front door criterion. It's pretty much the same. I put integrals in here, don't get scared. I put integrals in here instead of summations because I'm using continuous variables, but the truth is that these are summations over the values of MG and of T prime. And kind of to complement what I was just saying before, none of these neural networks or neural network adaptations would be able to estimate these causal effects given that you have such a causal graph. So I'd like to think about this project of ours as a bit of a generalization somehow of some of the work that has been done before. Okay, let me see. I saw a question before I go. Wondering about applicability of causality inference approach to time series. Absolutely, but yes, so I will try to be, I think I don't have that much time, so I'll go first to finish the presentation and then answer this question. But yes, I think it's a great question, always applicability. And yeah, so you have, okay, so one thing I wanted to tell you before, so this is, in this case, we see that we have these integrals, so you can't just sum over the values of mg or t prime. So in this case, what we came up with is just basically Monte Carlo integration. So basically, if you have this network that generates this t prime, and this generates it from a network that just takes a 1, so basically no parents, because we're assuming that we're not observing this parent. In here, we just take samples from whatever distribution is generated. And in the same way, for this mg variable, which is called a mediator variable in the causal inference literature, we just take samples from the neural network that took t as input. All right, so these are kind of how the variables were generated. Again, everything is very nonlinear, so you have some trigonometric functions, some squares, some inverse. And then in theory, this would be, from a linear perspective, this is impossible to get. And let's see what we got in here. So on the leftmost graph, we have the linear effect. So basically the blue ones are the distributions that we're finding. And of course, they're pretty much the same because they have the same effect. Then if we see the neural approach, we see that they're way closer. And this more than actual baseline, this is more of a tale of caution. And that's basically take into account that you can't just condition on stuff. Because if you condition on stuff, then whenever you want to see what are actually the interventional distributions, you are not going to get anything. So it's going to be very off. So actually it's better to do a linear model, but a linear causal model than conditioning on a variable. And then you have these WDs in here. They are just basically the Wasserstein distance between these two distributions, and the lower, the better. So you can see that these two are the lowest. So we got some interesting and nice results. Okay, so just a sip of water. Now, some logical steps which we could do is, for instance, extend this model to structural causal models and do counterfactuals, which was the third ladder of the hierarchy of causation. This is done. I was working on this already, and I saw that 2 papers got already released on the matter, and they used images, which is very, very nice. And they used images. They take the image as the whole input, and they, for instance, use the age of the people, and they use some other interesting stuff. I can share also the references if you're interested in this. They were accepted in NeurIPS for 2020. But other things that people are not looking at the moment is basically, for instance, checking what is the data and computational efficiency. So Claudio asked before, what do you win in here if you did some shared representation, and would it be better or not? Well, maybe in the causal setting, so if you're already imputing the causal graph, there will be some small gain. But most importantly, I think is, what if we actually have the causal graph and if we don't have the causal graph? So whenever we're conditioning on other variables, would it be better to learn our neural networks in such a way? This is something that hasn't been studied very much in the neural networks literature, but this is something that could be very interesting. And maybe this will solve partially, at least, the data problem in neural networks, which of course you're all aware that neural networks need huge amount of data to be trained properly. Maybe this can be a bit of a solution. And on the other hand, computation efficiency, if you have good data and then if you have the causal graph, I would expect, at least, this I can't say for sure, but I would expect that the number of training epochs to train a neural network to get some certain loss would be lower. Okay, thank you very much for listening. I hope that you like this causal story and how to mix them with neural networks. Now let me take Hayden's question, and then we can make other questions if you want. All right, so maybe out of scope, wondering about applicability of causal inference approach to time series, for instance, finance, population, migratory patterns, and climate, some data sets and some modeling. So yes, actually the team I am working with at the moment is it's working with a lot of time series, and I recommend you, I can write it to you here. This is called the Granger causality. So this is a very known model to even detect cause from effect in time series. This is also used in economics. And then basically, but this is not neural network related. So this neural network related is still very much in the kind of research phase, but not in the application. But usually what you do with this Granger causality is that you use an autoregressive model. So you use, let's say, a linear function of y given x in the past and y in the past, let's say, and then you do the same with x. So you do x with y in the past and x in the past, and then if x Granger causes y, then the coefficients of x are going to be significative, if you like that, or maybe in Bayesian setting, then they will be, the posterior will be far from zero. And if y doesn't Granger cause x, then the coefficients of the second estimation that you did will be close to zero. But then there are some subtleties in there. For example, that if you have a confounder, as I said before, then they might both Granger cause each other, or there might be a causal graph, which is, you know, causing each other, dynamically causing each other. If you're interested, absolutely send me an email. I'm going to copy my email in here. And then I can also send way more references to everyone if anyone is interested in maybe collaborating even, or they want to know more about anything. I do have a blog site, but it's very updated. I'm a bit embarrassed to share it. I will promise all of you that are going to check it that I'm going to improve it. Yes, last time I did it was a long time ago, but hopefully I'll start publishing a bit more in my blog. Okay, does anyone else have more questions? Either about causality, either about autoregressive density, or the project itself? Are we good on time? Claudio, was it good?
Yeah.
Okay.
I mean, we still have time for question, open discussion, and so on.
Great.
So if anyone wants to jump in.
Yeah, I think I inundated with a lot of information, causality and neural autoregressive, so there's a lot of things to think about. I hope it was somewhat clear. And by the way, Hayden, also about climate modeling, I remember now, NeoRIPS last year, so NeoRIPS 2019, they hosted a competition on causal inference in climate. So they were, the idea was to infer cause from effect, basically, in some climate data sets. And it was very, very cool stuff. And the winners did a very nice job, and they did something similar to what I said about this Granger causality. They use kind of a stylized version of that.
There is also, I don't remember the name of it, but it's a competition with a lot of papers in time series, and they post the best models each year. I don't know what is its name, but there you can find a lot of models.
Yeah,
a lot of models.
I think Uber won that once, no?
Yeah, exactly. Uber won,
yeah. I remember from their blog, they had a nice blog post about it.
Yeah, it was, I don't remember the model, but it was a combination, I think, of two models.
Yeah. I'm going to look it up right now. I'm going to see. So this is NeoRIPS climate.
You mean that paper about climate change where they recommended models?
There is also a workshop.
Tackling.
There is a workshop at NeoRIPS on tackling climate change with machine learning.
Yeah.
Yeah.
This one in here.
So I'll make a little bit of publicity.
Yeah.
Because we are organizing NeoRIPS meetups. They
Okay.
encourage this for people not taking the plane and go to Canada. And anyway, this year is fully online, the conference. So we are searching for people who are willing to watch with us some tracks from NeoRIPS in December. So if there are people interested, please write us on a meetup or Facebook or an email. So this could be one workshop to watch how to tackle climate change with machine learning, if there are people, of course, interested.
We had the last year 3 days, right, Robert?
Yes. Mostly on Bayesian.
Yeah, on Bayesian
learning.
Statistics, deep learning. Yeah.
That's the real statistics.
Yeah.
Frequencies for the winter.
I'm sorry, I'm going to answer Hayden's question. So on slide 21, with the top right and the top and the bottom right graph, we were conditioning instead of doing the interventional distribution. So instead of doing either backdoor adjustment or front door adjustment. So what happens when you condition instead of intervening is that you get some things that are very, very off. I hope that makes sense. And yes, this was again the cautionary tale, basically, in which if you condition only and then if you do only like purely blind data-driven stuff, sometimes it's not going to work. Of course, this is always depending on the application that you're looking for. So if you are only working in systems in which you will never intervene, so then it doesn't make that much sense to do this causal stuff. But in some settings, for instance, medical settings in which you can actually do some interventions, or even, for instance, reinforcement learning is an area that now is very hot with causality, then you can use some of these methods.
Maybe because we opened the discussion about Bayesian, do you know from your experience how they approximate, or what are they using to approximate the prior? Usually.
What do you mean approximating prior?
So like you have the initial prior, and what do you use to get the posterior, the first posterior? What do you use as a first prior?
That's always a difficult question, but I like Andrew Gelman take on this stuff. So the approach that I've been using and that people use whenever you have no priors at all, let's say, is that you use what are called weakly informative priors. So first of all, you make your data scale free and like you standardize your data. You subtract the mean and the variance and divide the variance or the standard deviation, I'm sorry. And then you use, well, depending on the model, of course, always, but if you use up parameters of a linear regression, let's say, then you would go for a normal 0, 1. And that usually works very well for scale-free parameters. It works very well, but there is a paper, very nice paper. I can write you the name in here, which is called the prior. The prior can only be understood in the context of the likelihood, which is that if you're using, this is Gelman, if you're using, whenever you're trying out priors, the best way to go is actually to simulate data and then see what is the output data and see whether that output data makes sense at all. And this is, for me, this is kind of super enlightening. And for me, it was very difficult when I was trying to understand this Bayesian stuff. In economics, they don't teach at all about Bayesian stuff. So it's mostly frequentist econometrics, least squares all the way. And when I was trying to understand this, I was asking myself all the time, okay, where am I going to get the priors from? These are, values of parameters. This is impossible. But if you go with the data simulation approach, it's always the best. And then there's also very nice paper that is called Visualization in Bayesian Workflow. And they give an example in there, and the example is that he was, I think this is with Aki Vehtari, they were modeling some density of particulate matter in the air. And they had some prior at the beginning, let's say, and when they simulated data, they realized that that some of the values of the densities that they were getting at the end were, so you had density of particulate matter in the air that were denser than a black hole. And of course that, you know, this is ridiculous. And then if you use a bit of this knowledge that you have, like some expert knowledge, you know that particulate matter on the air, in the air, can't be as dense as a black hole, then you can adjust the priors so that they, even before doing any use of the data, so only with what you know about the problem, the priors make sense in the context of the problem itself. So yes, whenever you want to use priors, my advice would be simulate data and see whether your data makes sense.
Great, yeah.
Yeah.
Okay, so I guess if there aren't any more questions, I think we can call it a day.
Thank you very much for the invitation. I'm very honored and thank you for the questions as well. It was very nice to present. Yeah,
it was a very good presentation. I think we all thank you for this.
Have a good night.
And maybe as a short announcement, all the content, I mean, will be shared on our Git. I mean, the presentation and maybe even the recording of this will be uploaded.
Also on Strasbourg deep learning.
And really, I have no problem with people sending me emails, and I tend to answer, I always answer my emails. So if you have more questions, or if you want to know more about it, want some references, maybe you want, I don't know, even to collaborate, then I'm always up for this type of emails. Thank you very much. Have a great night.
Thank you, Sergio. Okay.
Bye.
Bye-bye.
Thank you. Bye.
Thank you. Bye.
Thank you. Goodbye.